This assignment problem is a complex one. It involves entropy, it involves enthalpy, it involves Gibbs free energy, and even bond energy. So let's go over it, see how all these work together to tell us a lot about thermodynamics of a chemical reaction. This starts off with a table, a thermodynamics table, typically one that you'll find on an AP FRQ question or even an MC question. Notice that the two substances we're dealing with are oxygen and ozone, allotropes of one another. The table has got a blank in it, which is surprising. You think it's an omission, but it's on a thermodynamics table. When you're dealing with enthalpy of formations, you won't find enthalpies of formations of elements. In this case, oxygen is an element in its most common form. When you get oxygen, it's usually in the form of O2. The definition of an enthalpy of formation, the change in potential energy when a substance is formed from its elements, is just that. It's what change in enthalpy do you have, potential energy, when you make this substance from its elements. Well, if you're starting with an element, oxygen gas, making it into oxygen gas doesn't involve anything. So the answer is going to be zero. You're expected to know that. In fact, it's really nice to have elements in these thermodynamics problems because you have a value of zero. It makes calculation a lot easier. Now, the other values are not going to be zero because even though this is an element, oxygen, it's not its most common form. It's an allotrope of it. And let's take a little diversion to learn a little bit about ozone because it's an important substance where we've got oxygen, oxygen, oxygen. It's a common name is ozone. When they first discovered it, it was quite smelly. Well, it still is smelly. You can smell it down to 1 part per million. They say it's supposed to be reminiscent of chlorine, but it's, I think, a little bit more accurate. If you run electrical equipment, especially DC motors, you may end up smelling this little sharp odor, and that's because some ozone is being generated. Very distinctive. And so the name, when they first discovered it, was smelly. Probably should call it trioxygen now, but very often when a compound is discovered and gets a common name, it's kept it that way. So students have to know what ozone is. If we use trioxygen, you wouldn't have to remember its formula. O3, pale blue gas, but it's not usually found concentrated enough to be visible as a blue gas because if you get too much of it together, it'll explode. It's very unstable. At room temperature, it's got a half-life of about 20 minutes. So if you make some ozone and keep it at room temperature, you're going to be losing half of it every 20 minutes. If you get it down to 112 degrees below zero, it'll turn into a liquid. Our little treat at the end of this video is seeing some liquid ozone explode. It's very useful. Water is sanitized using ozone because it's so reactive. You can bubble it through water and it'll kill bacteria. It's used by municipalities to make our water safer to drink. By the time we get it, the ozone is gone. You can generate ozone by having oxygen, air, flow by a ultraviolet light. This is a pretty short wavelength, 185 nanometers. The photon's got a lot of energy. It can convert oxygen into ozone. And here's an ozone machine. The purpose in this case is to take odors and smelly areas and sanitize them. Ozone's much better than oxygen at oxidizing substances, and a lot of the materials that provide odors and smells, when they're oxidized, are wiped out. You can't smell them anymore. So it's pretty effective at that. In fact, that's why they sell these. When they sell them, they also sell you a no entry hanger to put on doors because you don't want to be in a room with a lot of ozone in it. It'll destroy you in addition to the odors. Whenever you've got the ozone treatment in progress, nobody should be present in that room. Afterwards, it's ventilated out and it just decomposes on its own. So within an hour and a half, much smaller concentrations of ozone. In the upper atmosphere, it shields us from ultraviolet, but down in the lower atmosphere, it is very irritating. It's considered to be a pollutant that you have to worry about in areas where you've got a lot of nitrous oxides that are produced by high temperature flames, where that nitrogen dioxide is changed to nitrogen monoxide, which then generates the ozone, and you've got a pollution problem. That's our little lecture on ozone. So let's get back to our problem. Using the data from the thermodynamic table shown above that you completed because you know that any enthalpy of formation, change in potential energy of an element, is zero. Calculate the change in entropy and the change in enthalpy for the decomposition of ozone to oxygen. You're given a table, and you know to find the enthalpy of a given reaction, you find the enthalpy of formation of the products, which we have in the table here, both of them now. If you didn't know about the zero, you'd be stymied. You wouldn't know what to do. So remember, elements, enthalpy of formation is zero, minus enthalpy of formation of reactants. This is, as in most change reactions, it's what you end up with minus what you started with. Easy to make a mistake because the reaction is written with the reactants first, and the equation's got the reactants last. So let's put the numbers in. We'll start with our ozone, which we've got here as a reactant. So I'll write that down right there, 142 kilojoules. Be very, very careful with signs. The signs are absolutely critical. It'd be a pity to go through all these calculations and lose the point because you forgot the sign. To make ozone, you've got to dump energy in. You've got to use that UV light or an electrical discharge to add the extra kinetic energy to move that potential energy of the molecule up. Our oxygen, of course, is going to be nice because we've got a zero. And so there's no problem with the oxygen. We can pretty much eliminate it. But let's keep on going with this because we have to include the coefficients. 2 moles of ozone, not just 142 kilojoules, 2 times that. And then we've got 3 oxygens, but of course 3 times 0 is pretty easy. 2 times 142, but again, the signs. We have a subtraction because this is a difference. And this 2 times 142 will also end up having a negative sign. The change in energy for this reaction is negative 284 kilojoules per mole of reaction as written. The AP convention for this is that these coefficients are basically the moles that this change in enthalpy is based on. That's quite a bit of energy, and as we'll see, this explosion, this release of kinetic energy, because when you change the ozone, this potential energy that was put in to make this ozone is released when you get to the lower potential oxygen. In fact, this is why ozone is such a reactive molecule. It's got all this stored potential energy. It's like a super oxidizer. We've done enthalpy before. This is really back to our earlier section on thermodynamics. But now we've included entropy. Whenever we did enthalpy, we had to have a change because you would never really figure out the total amount of stored energy in a substance. But amazingly, we can actually define and figure out the actual amount of dispersion of energy in matter using this entropy. And it's in joules per mole Kelvin. Because the lowest possible entropy is the perfect crystal at absolute zero. We have the zero. Everything after that will have a higher entropy. So you're always going to have positive values for entropy. So we've got to be careful. We've got to do our product first and then our reactant second. So our reactant is ozone. That's 238 joules per Kelvin. Next to signs, the joules versus kilojoules are the other big Achilles heel in student calculations for thermodynamics. So be very careful with that. Include the unit. Don't write down 238. Write down 238 joules per Kelvin. And of course, there's going to be a subtraction involved. And then our oxygen isn't zero because it does have a dispersion of matter and energy. It has that extra entropy. Nothing's going to have zero entropy. So we have our 205. And again, we've got a negative sign. We've got some multiplication. Toss in my numbers. It's 3 times our 205 joules minus our 238. But don't forget to multiply it by 2 because we've got 2 moles of that ozone. And I can double check. Yeah, I've got my coefficients. I got my subtraction sign. That gives us 139, which is an increase in entropy. And you say, wait a second, an increase in entropy, does that make sense? Yes. Look, we're starting with 2 molecules here, and now we get 3. we have a greater dispersion of matter. Before, these ozones are concentrated together as just 2 moles, and now we got 3 moles. So yes, that makes sense. An increase in entropy. Always look to see if your number makes sense. You knew that ozone is very reactive. It's explosive when it turns into oxygen, so that's got to be exothermic. You know that you're making greater numbers of particles, so therefore we have to have an increase in entropy. You have to include the unit in your answers. If you just wrote down negative 248, the reader would have to say, did he mean joules or kilojoules? So that's an absolute must. Joules per Kelvin, same thing. In fact, sometimes they'll even award a point just for the correct unit. You could have the wrong number, but if you had joules per Kelvin, you get a point on the AP exam. Wow, nice. Okay, now viewing this reaction in terms of enthalpy, the reaction would be thermodynamically. This is negative 284 kilojoules. This is the rock rolling down the hill. That happens on pretty much on its own. In terms of thermodynamically favored, yes, this is something that we would expect to occur, definitely. So this is thermodynamically favored. What most textbooks they call it spontaneous, but in AP chemistry, I've got the tongue twister to say, and it's what you should write when you end up answering any FRQ. Now, let's go to the next part. Viewing the reaction in terms of change in bonds. Bond energy. Oh, I really wish they would say bond breaking energy. The energy needed to break bonds, but they don't. It would be so nice if, in terms of teaching, if they say bond breaking energy, BBE, instead of just B. So we start with ozone. Here's a diagram, and we look at it. We see here we've got 2 molecules changing into 3 molecules. In the reaction, how did the bonds change? Well, we broke 2 of these sigma bonds, and then we formed a sigma and a pi. So we changed the bonds. Now, in terms of energy, this is very often something you really have to fight to understand. Here's some things you should know about exothermic reactions. We start with reactants, and the bonds of our reactants are weaker than the bonds of our products. This is true for all thermodynamic reactions. You form stronger bonds. We start with weak bonds. The oxygens aren't tied together as well as they could be, and then they form a stronger bond. In fact, again, this is why the ozone is so reactive. The ozone has a lower bond energy. These bonds are easier to break, so they have a lower bond energy. And then we make these stronger bonds, which have a greater bond energy. In all exothermic reactions, we go from lower bond energy to greater bond energy. This is a copy of one of the flashcards or study cards that you'll get at the end of my course. There's over 400 of them. There's always a question on bond energy that's supremely confusing. I read them over 2 or 3 times. We start with weaker bonds, but greater potential energy, because these have the potential to roll downhill. And when they roll downhill, kabam, a photon of kinetic energy is released as these bonds snap together. Imagine 2 magnets snapping together, making a stronger bond. You hear that snap. In this case, we get a photon of energy, and at the end of the video, you'll see those photons. So this drop of potential energy, a negative 284 kilojoules per 2 moles of ozone to make 3 moles of oxygen. That little drop means our products, our oxygen, have got less potential. You don't have to evacuate a room because it's filled with oxygen. You got to evacuate a room because it's filled with ozone. And if it's more than 200 parts per million, run. Based on the change in enthalpy, what is the change in bond energy? The change in bond energy will be the opposite sign of the exothermic reaction. So it will be positive. In fact, the equation for bond energy and enthalpy, the change in enthalpy is going to be equal to the bond energy of the reactants minus the products. It's the only equation where you've got reactants minus products. Okay, now let's deal with this entropy part. view the reaction in terms of change in entropy. The reaction would be considered thermodynamically, is it favored or not favored? The general rule is that the entropy of the universe is constantly increasing. So this, let's see, plus 139 joules per Kelvin. Yep, that's good. You have an increase in entropy that is thermodynamically favored. So without doubt, we have an increase of entropy, which is thermodynamically favored. So we got two things going for us. No wonder this stuff explodes. We've got a exothermic reaction rolling downhill. We've got an increase in entropy, and the entropy of the universe tends to increase. Which explanation for the change in entropy would consider to be correct on the AP exam? Now, I set up some choices here, and I set them up on purpose. One is an answer that is correct. The products, the oxygen, are linear and nonpolar, and the reactants are nonlinear, bent, 120 degrees, trigonal planar, and polar. This is true, but that doesn't answer the question. So this is wrong. You can say the products have a greater degree of randomness than their reactants. And that's what a lot of people say, and I would have marked it correct, but the AP doesn't. I talked to some graders. They decided that randomness is too vague. So unfortunately, even though this would be correct on many, many other classes, you can't use the term randomness. And I've been trying to not use it, even though I naturally default to it. Even the degree of disorder might not be good enough. Use the terminology that the AP uses, which is the increase in the number of particles results in a greater dispersion of matter. In AP, entropy is the dispersion of matter. That's the way to answer the question. Based on the change in enthalpy and entropy, what about the Gibbs free energy? The Gibbs free energy is the final say as to whether something really is going to happen or has the potential to happen to make products. And when that delta G is negative, we end up having a reaction that's eventually going to occur and produce products. The entropy increasing, we've got our potential energy decreasing. We're going to have a negative from change in enthalpy, and we're going to get a negative because of the subtraction, because of the increase in entropy. So this reaction will be thermodynamically favored because we have both factors, enthalpy and entropy, going for it. Now, if there's a conflict, our temperature will tell us, because it's a multiplier, who's going to win. Okay, what's the Gibbs free energy? Take our negative 248 kilojoules. Don't forget the subtraction sign. Multiply by the Kelvin, and then multiply by the change in entropy. And this is where I warned you about units. When you look at the table, all the entropy tables are in joules, but we're going to need kilojoules. You can't take kilojoules and subtract it from joules. You've got to have the same unit. So as a result, you can't use the 139 joules. You have to use the 0.139 kilojoules per Kelvin. Kelvins cancel out, and we get kilojoules for our delta G. Again, warning, warning, warning. The entropy is in joules, but enthalpy is in kilojoules, and almost always delta G is in kilojoules. Calculator, 284. Now we have a subtraction. 298, that's standard temperature, that room temperature, 298 kelvins, 25 Celsius. Multiply by, you could do 139 divided by 1,000. I'm going to put in, it's simpler, 0.139. My signs are correct. My change in entropy was positive. My enthalpy was negative, and I put that subtraction in there, 325, and the answer is going to be kilojoules. You got to put the kilojoules in, and that will be our answer for the Gibbs free energy. The next question. Oh, there's this little arrow that doesn't belong there. Ignore that arrow. Based on the Gibbs free energy, what will be the value of the equilibrium constant for this reaction? Now, equilibrium constant tells us the ratio of products to reactants. I said this reaction is thermodynamically favored. If we start with 1 molar of everything, if we start with 1 molar oxygen and 1 molar ozone, then in the end, this reaction is going to go forward and release that, let me get that calculator back up again, 325 kilojoules. So not only do we get energy from the change in entropy, we get this energy from the dispersion of matter. I mean, this is 325. You can do stuff with this. You could use ozone as a fuel if it weren't so dangerous. So in the end, we're not going to have any ozone. Our ozone is going to be gone, changed into oxygen. So the K is going to be a large value. It's going to be positive. So whenever you've got a negative delta G, thermodynamically favored, it favors the products. Therefore, our K, which is products over reactants as a ratio, we're going to have a value that's larger than 1. Here's the equation. It is taking E, our lovely E, Euler's constant. Then we've got a negative sign to change the sign of delta G. This negative 325 is going to be a plus 325 with this extra negative. Remember, I warned you about the signs. And notice I've set this up with the 2.5 kilojoules per mole. E to the x, second function, natural log, take a negative, and then pull back my answer that I had, divide it by 2.5, and see what we get as an answer. Whoa, this is a huge value. The number of atoms in the entire planet of Earth, I mean, if you took every atom in every compound in the entire planet, from the atmosphere down to the core, you'd only get about 10 to the 50 atoms. So this equilibrium constant is so great that all this ozone eventually is going to be changed into oxygen. In terms of answering this on an AP test, they give you a huge latitude for your answer because it is so large. So if you said 10 to the 50, you get the right answer. In fact, they'll even give you the answer correctly if you just have E raised to the correct power. Now, the last question here is a trick question, and it's based on something you've got to be careful with. We talk about rate constants, and we use the lowercase k for it. The rate constant tells you how quickly something is going to happen, not if it will end up happening. You can have some thermodynamically favored reactions that are so slow that you'd have to wait till the end of the universe for anything to end up happening. In the case of diamonds and graphite, diamonds are not thermodynamically favored. Graphite is. So diamonds should be changing, exploding into graphite, but it has such a high activation energy that it's not going to happen at a rate that is discernible unless you increase the temperature to thousands of Kelvin. So we've covered everything from A to G on this problem. Let's take a neat break and watch ChemForce apply some activation energy to liquid ozone to have it explode and release those photons. So take it, ChemForce.
Hey guys, in this video I'll show you a very interesting frame I managed to capture while making a video about the explosive decomposition of ozone into oxygen. So, to demonstrate an explosive self-decomposition of liquid ozone, I will hit on the tip of the ozone-resistant silicon tube where liquid ozone drops gather. Filming at 120 fps, I managed to capture a peculiar frame. The moment the explosion occurred and ozone changed into oxygen, the whole tube got filled with bright light. The change between allotropic modifications followed by the glow is an extremely rare phenomenon in chemistry.